Welcome back. This is part 5 and is one of the most important concepts to understand in this series. In this tutorial, we will learn what posterior predictive distribution is and, more importantly, what it represents. The content and the example used is inspired from chapter 1 of Dr. Bishop's book. And before we go any further, let's do a quick recap of what has happened so far. We started our discussion by comparing various linear models, the linear models using different polynomials of various orders. We noticed that a more capable model called M9 overfitted. That is, it worked well on training data set, but not so well on test data. We tried two remedies. First one was to increase the size of the data set and it worked. But then we wanted to make the model work with smaller data set as well. To do so, we used what is called ridge regression that applies the regularization to the weights. I explained how to interpret and construct the sum squared error function, and even though all reasons were valid, it felt forced. In the second part, we started with a different viewpoint and also added an additional requirement. We argued for our predictions to be random variables. This way they have distribution instead of being point estimates. We ended up learning maximum likelihood estimation and more importantly saw that the sum squared error function now naturally occurred. We concluded that the linear regression with sum squared error is a special case of maximum likelihood estimation when we assume Gaussian noise. It was the first step where we introduced the random variables in our exercises. In part 3, we took our first baby steps towards including the Bayesian view on the problem. In Bayesian model, we want to see all unknown variables as random variables. This means we started to see our weight vector as a random variable and used Bayes' rule to get its posterior distribution. Bayes' rule enables us to express our belief in the random variables without seeing the data and then update this belief when we observe data. This updated belief is called posterior distribution. We saw that both sum squared error function and the ridge regression's regularization terms now naturally occurred without any crafty justification. And when the time came to use the weight distribution, we made the choice to go with the most probable value of weights. In part 4, we went over the rules of probability and more specifically learned how they can be used to compute joint, marginal, and conditional probabilities. The tutorial for today makes use of these rules. So if you are not well versed in these rules and or require a refresher, I would recommend watching the part 4. So now we move on to the topic for today. I start by writing the posterior distribution of weights that we had obtained in the part 3 of this series. I had mentioned in part 3 that unfortunately the notations are often not used consistently. And I believe that it is also one of the reasons learning in general is hard. This problem, however, is not limited to this field. So it's not that it is specific only to this subject or this field of science. Now, in this equation that I have on the screen, alpha and beta are scalar values and are also our hyperparameters. Since these are not variables, these are fixed values, these are hyperparameters, they are not going to change. Quite many times you would not see them included in the equations and their presence is implied. And therefore I am removing them as well. In the book, Dr. Bishop also ends up removing them. However, he is not very consistent with the notation. At some places he includes them while at other places he does not. So please take this into consideration when you're reading the book and even other articles or books on this subject. That said, the goal of modeling is to be able to do prediction on the new data. To do the prediction, we need the values of the weight vector. And the dilemma here is which value of W should we use? We had the same dilemma in the part 3 and we agreed upon, or rather I forced on you to choose the most probable value. Most probable value means the mode of the distribution. Towards the end of the part 3, I had said that we have taken good baby steps towards treating all unknown variables as random variables, but it is still not a proper Bayesian treatment. So here we are challenging the usage of mode. As such, you could ask why mode and not median, or even why not the mean value. You see, all these are summary statistics of our model. They are point estimates that convey some information about the distribution. However, I am afraid if I go and explain all of this, I will go on a different tangent if I touch these aspects of why none of them are ideal. So, to keep it brief, the usage of mode, mean, and median is dependent on the model and the problem, and even more so on a well-defined objective or a loss function. And quite often, even in those well-defined cases, you would be ignoring the information that the posterior distribution aims to provide. You see, summary after all is a summary. Since we now have the entire distribution available, not using it is like leaving the information on the table. Given all this, maybe we ought to rephrase our question or ask a better one. And here is one such attempt. The reason that we made our weights the random variables was so that we can use the uncertainty that they would provide. Let's first see how the book answers this question. According to the clipping from the book here, it is about consistent application of sum and product rules of probability. And while it is correct, I'm not sure if this phrasing helps in building the intuition of what exactly is a Bayesian treatment. And on top of that, even the application of these so-called rules is not so obvious in this formulation. At least it was not to me the first time I had read the book. And this is where I will focus today to help you distill out both the intuition and the derivation of this object and thereby the Bayesian treatment. Essentially, we will use the concepts of marginalization and expectation to explain this proper Bayesian treatment. Now, if you are not well versed in marginalization and expectation, my previous sentence will not be more useful than what this clipping is saying. So let's build all of this first without the usage of fancy terminology and intimidating mathematical formulations. However, we still would like to tame this mathematical formulation and see how it came into existence. Now the term marginalization means that we are summing or integrating over all possible values of W. The summing or integrating implies that we are taking into consideration all the possible values of W. If you can take into consideration all possible values of W instead of summaries like mean, mode, and median, then our predictions will be more grounded and possibly more consistent. Now, expectation is an easier concept as it represents the weighted average. Unlike the traditional average, where the contribution of all the elements towards the average are same, in weighted averages, the contribution towards the average or the mean is in proportion of the probability or the weightage of the elements. Since there are many values of W now, because it's a random variable, not all of them have the same weightage or same contribution. So now we are combining both these concepts, the marginalization and expectation, and what we are saying is that we want to consider all the values of weights, but still take into consideration their respective probabilities. I will explain and dwell more on this in next few minutes. Here I have extracted the formulation from the snippet from the book. Remember that I use bold lowercase letters with orange color to indicate the vectors. Before I go further, I want to label the components of this formulation. The left-hand side is called posterior predictive distribution. The last term in the right-hand side is the posterior distribution of weights. We have seen this guy already. We have it when we did the part 3. And the remaining term is called the likelihood function. I'm now going to explain both the left-hand side and the right-hand side using the lenses of marginalization and expected value respectively. Let's start with the left-hand side. We can read it as if we are asking a question on what should be our prediction distribution given the new observation and the data set. The data set here is represented using the orange colored x and t, that is our independent variables, and the dependent variable t. The x, which is not colored and which does not look like a vector, is a new observation, and the t is the corresponding target variable that we are supposed to get. Or in this case, really, we are interested in getting the distribution of the target. This is okay, but then where is the model in this formulation? We don't see any w here. Because when I say model, one of the key actor is the weight random variable that ties these independent variables and the target variables. You should appreciate here is that we'll not be able to get the predictive distribution without the model. Just the data set is not sufficient. This means that there is more to this left-hand side than the simple interpretation that I gave earlier, which is what is a prediction giving new observation and data set. Simply put, it does not talk about the model. So there is something missing in here. Let me first bring our question here so that we do not forget about it. You see, our primary goal here is to include the uncertainty in W when we will make the predictive distribution. And here the way it is written, there is not even a W there. The way we think about now is that we ought to see our prediction process itself as a joint distribution of T and W. And thinking in terms of prediction process that consists of two random variables, T and W, is good. But then when we want to get the prediction, that is T, we have to marginalize the weight variable. I know what you're thinking. All these statements are equivalent. Unfortunately, there is no consensus on the grammar here. Some say we integrate the variable out. Some others say that we integrate over it. And of course, we say that we are doing the marginalization. But the most important thing here is that we should see the prediction process as the joint distribution of T and W, and which means that the posterior predictive here represents the marginal distribution where we have integrated over W random variable. Just a quick refresher here. This is essentially what I had explained in part 4, that is the rules of probability. In there, I had two discrete random variables, x and y, that define our process. X can attain one of 5 states, y can attain one of 3 states. The grid or the table shows the number of times the various combinations of states of x and y occurred. Now, using all this information, we can compute the joint probability of certain combination. Here I am showing you the probability of x being x4 and y being y2. However, the one that is of interest to us and the relevance to us to this particular discussion is the notion of marginal probability. Here we are interested only in the probability of x being in x4, but we know that our process requires both x and 4 to be present. x4 cannot occur in isolation. So when we are computing the marginal probabilities, we are considering all the possible values of the other random variable. The other random variable here being the y random variable. I hope now you can see that when I say that the posterior predictive distribution is nothing but the marginal probability distribution, it means that we must be summing over or integrating over the W, the weight random variable. Let me now write the left hand side in the form of the integral that shows the marginalization. As you can see that this integral is showing that all values of W will be considered. Another way to say is that we have applied the sum rule of probability. Sum rule for discrete random variable is represented as this, and for continuous random variable you replace summation symbol with an integral. Again, sorry, I'm saying it again, but if this is not making sense, I would recommend to watch part 4. As such, I made the part 4, that is the rules of probability, after I prepared the material for this tutorial. I had started to feel that understanding those rules is very important to get this concept understood. Now I will try to explain the right hand side of the equation. For that, here is a very brief explanation of weighted average of functions of random variable, also called the expected value or the expectation. I show here the formulation for both discrete and continuous random variables. Essentially, you take a sample X from a distribution indicated using P, the one that is on the rightmost side, the P with the subscript theta. You then evaluate this sample using a function indicated using H. However, when you are adding or integrating, you also need to consider the weight or the probability of that sample. In other words, the contribution of all samples from the distribution is not going to be same. It will be in accordance with their chances of happening. Given this, now if you look at the right hand side of our equation, you should see that it is nothing but an expectation formulation. The distribution from which the sample, in this case it will be W, comes is the posterior distribution. The function in which we feed the sampled value of W is the likelihood function. Different samples of W from the posterior distribution will have their respective probability of occurrence. So this way you can appreciate that this right hand side is nothing but the expected value formulation of the posterior predictive distribution. It's so important that I want to summarize it in few different words now. You should consider this entire thing as a 2 steps process. Step 1, for every W we will sample from the posterior distribution, we will have a corresponding prediction distribution. This means there will be not only one predictive distribution anymore. Every W will create a new one. Step 2, we then combine these predictive distributions according to the posterior probability of W. It is therefore the weighted average of possible predictive distributions. So this is the expectation view of this formulation. Now that both viewpoints have been explained, we still would like to see where this formulation comes from. How do you equate these two sides? This way, not only we will have an intuition behind the posterior predictive distribution, but we will also understand this mathematical formulation. So I start by writing the posterior predictive distribution first and foremost as the marginal distribution. I had derived and proved and hopefully convinced you of that in the previous slides. And that happened because we had applied the sum rule. Now comes the master stroke. I can apply the product rule on the joint distribution of T and W, which lets me express the joint distribution as the product of conditional and marginal distribution. This is again explained in part 4 of this series, where I had used a much more simpler example to show these kind of steps. In there, I was using a discrete random variable. Here, the only difference is that we are dealing with continuous random variables. All I have done is to switch places. I have just moved the first term to the right hand side. Now in the first term, we have t conditioned on w and the data set, that is x and t vectors. But we now make an argument that given w, the new prediction is actually independent of our data set. When you are making a prediction on a new observed independent variable, you do not need the data set. And by this get rid of them, we can remove them. And now, as you can see, we have the same formulation as that of Dr. Bishop. I hope this makes sense. We have indeed tamed the formulation, but there is still a danger lurking here. There is this damn integral. These integrals are scary beasts. They are the troublemakers. But for now, we have a way of getting around them. However, in later tutorials, we will have to face it head on. For now, we are ignoring them. And we can ignore them for now because we are in a configuration where the likelihood, the prior and posterior are all assumed to be Gaussian. As such, we have assumed likelihood and prior to be Gaussian, and the consequence is that the posterior is Gaussian. And also the consequence is that the posterior predictive distribution is also Gaussian. And therefore, this integral has an analytical solution. This analytical solution is possible because of the special properties of Gaussian distributions. When you add or multiply two Gaussian functions, you get another Gaussian. It takes about a page or two to sort this out, but in the end, you will have a Gaussian function for your posterior predictive distribution. This is what this clipping from the book is showing, and also showing what would be the mean and the covariance matrix of the resulting Gaussian distribution or the resulting posterior predictive distribution. Now I will show you some code snippets. The first one is simply about some functions and code to generate the underlying function and noisy training data. It is exactly the same as that what we had in the part 1. Now I'm using a helper function that generates the design matrix for the model of degree 9. To do so, we use the polynomial features class from scikit-learn. Again, this is something that we had done in part 1 as well. And here I am generating the noisy test data, a lot of test data as such. Since we have an analytical form of mean and variance available to us, I will now implement them in Python. Let me bring the clipping from the book so that you can see it alongside with the Python code. You can see that there is one-to-one correspondence between the equations in the clipping and the Python statements. The values of alpha and beta used here are the ones that were specified in figure 1.17 that I am trying to reproduce. And finally, we are doing the prediction on the test data using the mean that has incorporated the uncertainty in weights. I then plot it, and here is how it looks. This is the original sine curve. Here are the 10 noisy training data points. We are using model M9. This is the curve that uses the mean value from the posterior predictive distribution. It's quite nice. And we also show the plus minus 1 standard deviation area using the shaded portion. And this brings us to the end of our tutorial. So no more baby steps anymore. This time around we have all unknown variables as random variables, and more importantly we have managed to incorporate the uncertainty of our weight variables in our prediction. As such, the posterior predictive distribution is one of the main end goals of Bayesian modeling. I hope you now have both the intuition about it as well as the justification of its mathematical formulation. This all being said, we still have many problems and issues that we have not touched and talked about. I say so because from computational point of view, things have worked in our favor so far because of the usage of Gaussian distributions. You will not always have Gaussian distributions coming to your rescue. You will use different type of distributions for your prior and for your likelihood, and they would not necessarily have the same properties. So we must start to worry about this integral that we had seen. I will address all these kind of issues in upcoming tutorials in this series, and with that I thank you for the time you have spent here. Please write in comments the questions that you may have. Bye for now. See you in another tutorial. Bye bye.